Welcome to the video lecture on the electric drives. In this video, we are going to talk on the load equalization. When we represent the load here, we generally talk about a load having a constant load torque TL. Load which is having a moment of inertia JL, and it is having a constant load torque TL. But there are certain kind of load where, like pressing mill, electrical hammer, where the load torque is not a constant, rather it's frequently changing, and we are assuming that the load torque requirement is very high, then it is working at a no load. Then again it is working for a very high load, then again for a certain time, then it is working as a no load. So this is the electrical hammer. Suddenly the load is very high, then once the work is over, then you have the load is no load. So we are defining it like TLH for a high load and TLL for a low load. And x-axis, let us say the time, and for the heavy load the duration is, let us say, TH, and for the light load the duration is TL. Now thing is that the peak load is TLH, and if I will go for a suitable motor which is having a peak load of TLH, the cost will be very high. And with this type of load, let us say at the peak load the current is 20 amperes. The current requirement is, let us say, 20 ampere. At no load the current is, let us say, only 1 ampere. So what happens is, for a certain duration of time there is a sudden rise of current in the motor end. Let me say that is a motor over is here. Now this motor draws a current of 20 ampere for a very short time, then for another time it draws a current of 1 ampere. In that way, what will happen is, it will affect the source. If it draws the current, from the source, let us say if this is from AC, it is converted into DC, and that DC supply is given here. Suddenly the requirement is 20 ampere, then the requirement is 1, then again 20. This high inrush of current will affect the source voltage, because source is connected, source is having the inductance, the transmission line is having the inductance, and when there is a high rush of rate, di by dt is high, so L di by dt will obviously come into picture, and it will affect the source voltage and the others voltage across the other terminals, those are connected. So this way there is preferring a very high load for a short duration. There are two disadvantages there. One, the motor rating required will be very high, so the cost will increase. Second, this high inrush of current will affect the source, and the voltage there will be sudden down in the voltage, sag in the voltage. So this will pollute the supply source. To avoid these two things, what we can do is, we can couple it from a coupling shaft, we can connect it to a flywheel. We can connect it to the flywheel, and through the flywheel we can connect it to the load. Okay, so like through the flywheel we can connect it to the load like this. Correct. So what is the advantage of connecting a flywheel in this way? The two advantages that advantage is that we don't need a high rating of motor. Second, the spikes will be decreased, and let us understand how. To understand that, let us write the torque equation, that is Tm is equal to J d omega m by dt plus TL. This is a torque equation for this load, where J is equal to J0, that is the moment of inertia of this motor and the load, plus load is of JL, let us write JL also, plus this is initially there. Now we are adding a flywheel, that is JW. So here we have the motor torque is equal to dynamic torque plus load torque. This dynamic torque, J d omega by dt, is what we are going to use. Let us say we have suddenly there is a heavy load from 0 to T to TH. There is a sudden rise in the load. The load requirement is TLH. Now this heavy load will obviously try to decrease the speed. Motor is having a motor torque Tm running at omega m and load torque TL. So suddenly the torque requirement is TLH. Obviously there is a deceleration of the motor. Motor will get decelerated because earlier it is running at a steady state. Now it is get decelerated. Once it decelerated, this dynamic torque quantity d omega by dt will be negative. If this is negative, we can write Tm, this negative on the left hand side, it will come and it will be positive. Now this is equal to TLH. Now the equation suddenly changes. Now this dynamic load adds to the motor, dynamic load torque adds to the motor torque to fulfill the load torque. For the second case, during the time from 0 to TL, there is a light load. So during the light load period, this dynamic torque, light load period means there will be an acceleration. Load has suddenly becomes very low, so there will be acceleration. Because of this acceleration, this J d omega by dt will be positive, and when this is positive, Tm will be equal to J d omega m by dt plus TLL. Now this dynamic torque add with the load torque at the time of light load, and this dynamic torque add with the motor torque at the time of heavy load. So that is why we are just adding some extra inertia J, so that the flywheel inertia is added with the motor and the load inertia, so that the effect of dynamic torque can be increased and we can compensate. The motor torque is no longer required to fulfill the TLH. Rather, motor torque is now TLH minus J d omega m by dt. So we have got limitation now. We have got some advantage. The advantage is that now to the motor, the load torque will reflect not TLH, rather a T max. And the minimum is also not TLL, rather T min. So when you have a load is suddenly applied, you need to increase the motor torque will definitely try to increase. At steady state, it will look like it is rising from minimum to maximum and from maximum to minimum. Then from minimum to maximum, then maximum to minimum. indirectly we are no need to go for a high value of the motor rating, we are going for a lower value of motor rating, that is T max. And the fluctuation of the current because of sudden change of the load is also get reduced. So these are the two advantages of flywheel. There is a condition that this flywheel should not be used for a reversible motor drive. Reversible means if the motor is running in one direction, then only this flywheel is used. If the load requirement is of reversible in both the direction, then this flywheel should not be used. Now for this particular case, where we are running the motor in only one direction, adding a flywheel to it, let us calculate like what value of the J or JW we should use, so that for this particular motor T max can be the maximum rating. So let me just rewrite some of the points from here in the next slide. So here this circuit is been redrawn over here in the next slide, and this is what the motor torque required to be moved from T minimum to T maximum in this way. So the torque equation, let me rewrite the torque equation Tm, let me write as a function of time, is equal to d omega m as a function of time divided by dt plus TL as a function of time. For a particular time 0 to th, this TLT will be equal to TLH. Now we have an odd man over here, that is d omega m by dt. To write in terms of Tm, that means we would like to convert this d omega m by dt into dTm by dt. So a motor is also required to fulfill this purpose. Let us say this motor is having a speed omega m in the y-axis and torque Tm in the x-axis. For this particular case, if we take a DC shunt motor, so we have here DC shunt motor, which is supposed to have a constant speed, but because of the armature reaction, there will be slope and it is negative decaying. Let the initial speed or no load speed is omega m 0. Let it is running at a certain value depending on the steady state stability, or let us say this is the load torque TR. So based on the steady state stability, it is running at a certain load, and then you have this omega mr. So we can have the slope of this line is equal to K is equal to omega m0 minus omega mr divided by TR. And the equation of this line will be equals to omega m t is equal to, the slope is K, on the x-axis this is TMT, plus the constant is omega m0. One thing we left out, this is a negative slope, so it is minus of K. So let me rewrite this thing here. So what we get is omega mt is equal to minus of K TMT plus omega m0. Now let us do the derivative of this equation. For the initial one, this is equation 1. Let's have a derivative of this equation. What we get is d omega m by dt is equal to minus K dTm by dt. This is a constant, so it will be 0. So now we can substitute this value over here, and we can rewrite equation 1 as TMT is equal to minus of, I missed the one point over here, J. This is equation is complete now. It is equal to minus Kj dTm dt plus this TL t. Now this equation, let me rewrite. It's look like a single order equation, dt plus tmt is equal to tlt. Now this equation, I can assume this as a single order equation, like if I write tau dy by dt plus y is equal to some constant c. In this particular equation, it is TLT at a time 0 to TH. This is a fixed value TLH. So if this is the equation, we can write this equation output is equal to some constant A0 e to the power minus t by tau. A0 is this initial value. Plus the final value, that is obviously the constant value is the final value, and by the rate at which it is rising and trying to reach the final value, e to the power 1 minus e to the minus t by tau. This is the solution of the equation above it. So we were just trying to get the solution for our this equation. So for time t between 0 to th, right, we have the formula is tmt is plus, not this one, tau. Instead of, we can write tau, or we can write here jk dtmt by dt plus tmt is equal to tlt. So instead of writing tlt, we can write at this time the load is TLH. Now the solution is TMT is equal to initial value in this waveform is T minimum, right? So T minimum is the initial value. Let me just keep this picture over there also, right? So here we have the same picture over here. So TMT will be T minimum. So what is the minimum? Tau T minimum, and then e to the power minus t by tau, plus what is the final value it is supposed to achieve? TLH is the final value it is supposed to achieve. So TLH, then 1 minus e to the power minus t by tau. So if I substitute the value that at t equals to th, the final value that is achieved is T max. So we can write here T max is equal to T minimum e to the power t minus t by tau, TLH. Instead of writing here t by tau, we can write TH by tau. Like this. Now we will solve it. So after solving it, we can write to the power TH by tau is equal to these two terms we can take aside. We can write TLH minus T max, and these two terms we can take aside, that is TLH minus T minimum. And if I just remove this minus sign, if I remove this minus sign, this will be just interchange. So above will be T minimum and here will be T maximum. So what is the value of here tau? From this I can get the value of tau is equal to TH by ln of TLH minus T minimum by TLH minus T maximum. What we can see here is the TLH minus T minimum. TLH minus T minimum is the higher value, TLH minus T maximum is the lower value. So this is obviously greater than 1, ln of greater than 1 is positive number, so tau is obviously tau is a positive value. So tau is nothing but J into K. So K we can also get, because in the figure K is equal to omega m0 minus omega mr by tr. And if we know the TH and other terms, we can calculate the value of J. Now this for the same, for time 0 to, instead of having time 0 to TH, if we have a time from the time between 0 to t and tl, the same expression will be there. Only thing is that here tm, this expression of here will be changed. So tmt will be equals to, the initial value is no longer t minimum, the initial value is t maximum. T max, then e to the power minus t by tau dash. The slope tau dash is, if this is the constant tau, this side may not be the same, tau dash, plus what is the final value it is supposed to reach? TLL, and 1 minus e to the minus t by tau dash. Now finally at t equals to TL, what exactly the final value it reached? T minimum it reached. So we can write here T minimum is equal to T max e to the power minus TL, time taken in the load period, tau dash, TLL, 1 minus e to the power minus TL by tau dash. So from we can evaluate this and get the value in the same way. E to the power TL divided by tau is equal to, let me write minus first. So T minimum and TLL we can take it aside. TLL minus T, let me write T minimum minus TLL, minimum minus TLL, and here T max and TLL, so I can write T max minus TLL. So if I remove this negative sign, obviously there will be interchange of the position. So here upper one will be max, lower one will be minimum. So what is this T max minus TLL? T max minus TLL is the higher value. T min minus TLL is the lower value. It's higher to lower value, so we are adding positive term. So this implies that we can get the value of tau dash is equal to TL by ln of T max minus TLL divided by T minimum minus TLL. This we can get the value of tau, which is nothing but equals to same J and K, and we can calculate the value of anything is asked, we can calculate from this equation. So thus we understand that how to get the inertia if you know all the above data, and also we understand that what is the importance of flywheel, and most important point is flywheel we cannot install in a motor if we have a reversible drive. It is only, the condition is that if it is a forward motion only, then only you have to forward motion, then only you have a flywheel. And the advantage is that the rating of the motor no longer required a very high rating of TLH. We can have a lower rating of Tmax, and the source is, the current run from the source will no longer be very high. It will be only limited to a certain value, and the fluctuation is actually avoided, and that fluctuation avoided will stabilize the load supply voltage. So with this we have completed this load equalization, and this is what we call it load equalization, so that the fluctuation of the load is decreased. Thank you very much.